Raw business data, names, addresses, transaction values, flooding into a server without a plan leads to inconsistent records and system failures. Without a rigid architecture to manage the flow, information is easily duplicated or overwritten. A scalable production database cannot be built on the fly. Processing large volumes of information requires architectural planning to ensure the data remains accessible and accurate. Engineers manage this complexity using a framework known as the Database Lifecycle, or DBLC. This lifecycle consists of 6 phases: analysis, design, implementation, testing, operation, and maintenance. The cycle begins with analysis. In this phase, engineers examine existing systems to identify technical constraints and determine the exact scope of the business requirements. While every phase is necessary, the structural integrity of the entire system depends on the logic applied during the second step, design. The primary objective of the design phase is translating the business requirements gathered during analysis into a concrete data architecture. This happens in stages. Engineers create a conceptual overview first, which then guides the creation of the logical and physical designs. To map these designs out before the database is built, teams use a standardized visual language. They rely on entity relationship modeling, or ERM. This technique generates an abstract, visual representation of the data structure. ERM allows engineers to solve relationship problems on paper. Catching logic errors at this stage prevents data redundancy issues that would otherwise increase storage costs and slow down query speeds once the database is live. The transition from analysis to design starts by defining exactly what categories of data the business must store. We begin with entities, the foundational blocks of the database. A customer is a primary example of an entity. Because a single entity is too broad for a database to process, we break it down into attributes. For a customer, these attributes include first name, last name, postal address, and email. Every attribute is then assigned a strict data type, which tells the system how to interpret and store the incoming information. For the first name attribute, we assign a character or string data type, which ensures the field only accepts alphanumeric text. In contrast, a financial attribute like an order total is assigned a currency data type, so the system can perform mathematical calculations on the values. Enforcing strict data types at the entity level ensures machine readability and prevents invalid inputs from corrupting the records. Isolated entities cannot function as a system. An architecture requires mapping the connections between them. We establish connections between entities based on matching values. Let's look at 3 categories: employee, pay, and city. A one-to-one relationship exists when a pay ID in the employee table links to exactly one matching pay ID in the pay table. One-to-one relationships are used for specific purposes, such as isolating sensitive salary data to restrict access. The most common connection in database design is the one-to-many relationship. Here, a single city ID in the city table can be linked to multiple different customers who reside in that city. This allows the database to organize information hierarchically without repeating the city's full details for every single customer record. As data models grow more complex, engineers encounter a common design challenge: the many-to-many relationship. For example, many different customers can buy many different products, and any single product can be purchased by many different customers. Connecting these tables directly creates a logic gap, because there is no place to store data about the transaction itself, like the date or the quantity sold. This prevents the system from verifying that every order record points back to a valid customer and product, a standard known as referential integrity. To maintain these links accurately, engineers use a junction table. We insert an orders table to act as a bridge between customers and products. The customer ID from the customer table links to a matching field in the orders table. The product ID from the product table also links to a matching field in the orders table. The junction table resolves the conflict by turning one many-to-many relationship into 2 trackable one-to-many relationships. This completed map of entities and relationships is called an Entity Relationship Diagram, or ERD. The ERD is the visual result of the modeling process we just completed. Before the design is ready for implementation, the model undergoes schema refinement. This is achieved through normalization, which is the process of reorganizing the data to remove redundancy and ensure logical dependencies. Normalization requires that every piece of data is stored in exactly one place, and that related items are grouped together. This creates a single source of truth. If a customer's address changes, the system updates one cell to keep the database accurate. While a conceptual ERD proves the logic of the system, it lacks the technical detail needed for the actual build. The design must transition into a physical data model. This schematic includes technical specifics like byte sizes and server requirements for each table. The physical design shows exactly how the data will be implemented within the chosen database management system, or DBMS. Analysts use this model to calculate required server storage before moving to Phase 3, implementation. This is where the DBMS is installed and the data is imported. How easily a database is implemented depends on how thoroughly the schema was refined during the design phase. After the build, Phase 4 begins. In testing, the team tunes the system alongside its applications to ensure stability before going live. Phase 5 is operations. This is when the database is active in a production environment, providing reliable information to its users. The final phase is maintenance. Databases must adapt over time to handle heavier traffic or new data requirements. Scaling the system or adding new features is a manageable process if the data structure was properly normalized during the initial design. The database lifecycle is a continuous process. Its operational success relies on the structural logic established during the initial entity relationship modeling.